The calendar designated the month as June, but the thermal state of the ocean dictated a completely different structural reality. Somewhere over the open waters of the Philippine Sea, east of the island of Luzon, a thermodynamic event unfolded that completely broke the baseline expectations of the Western Pacific Cyclone Basin. A system that began the week as an unremarkable cluster of convective thunderstorms underwent a profound structural transformation, detonating into the most intense June typhoon this sector of the planet has manufactured in 22 years. Its international designation is Typhoon Mechala. The core paradox of this event does not lie merely in its current destructive capacity, but in the temporal misalignment of its architecture. The Western Pacific is objectively the most volatile and active tropical cyclone basin on Earth, yet its mechanical output operates on a strict seasonal schedule. The production of top-tier, high-density systems is historically reserved for the late summer window spanning August through October. This is the period when the upper oceanic layers have spent months absorbing solar radiation, maximizing heat storage, and priming the atmospheric column to allow us to reach its theoretical thermodynamic ceiling. June is traditionally characterized as the early season warm-up phase, generating weaker, disorganized, and structurally sloppy systems because the macro-environmental engine has not yet fully spun up. Mechala completely bypassed this mechanical constraint. To locate a direct historical precedent for a June anomaly of this magnitude, geophysical records require a retrospective leap of over 2 decades to the year 2004. An entire generation of tropical systems has passed through this basin without a single June storm matching these specific metrics. The true scale of this crisis is anchored in documented physical measurements, verified by agency data from the Joint Typhoon Warning Center, the Japan Meteorological Agency, and the Philippine Atmospheric Authority, Pagasa. Over a single 24-hour window, Mechala's maximum sustained winds surged by approximately 50 knots, equivalent to a velocity increase of nearly 60 miles per hour. In meteorological science, the formal threshold for rapid intensification is defined as a gain of 30 knots within 24 hours. Mechala did not merely cross this threshold, it nearly doubled it, accelerating through a 36-hour stretch to register a total intensity gain approaching 70 knots. This rate of development places the event in the extreme upper tail of historical statistical distributions. By the conclusion of this intensification burst, the system had structurally replicated the parameters of a major Category 4 hurricane, with central barometric pressures plunging to 935 hectopascals and sustained core winds clocked at 95 knots, or 50 meters per second. Official tracking projections indicate that the system's ceiling has not yet been reached, with forecast models extending its peak toward 130 knots. The critical boundary where a system transitions from a standard typhoon into a super typhoon. This rapid escalation exposes a profound systemic deficit within the current baseline state of the Pacific Ocean. An early-season super typhoon cannot be interpreted as an isolated, erratic weather event. It functions as a direct thermodynamic readout of the basin itself. The ocean is effectively showing its hand, revealing an unprecedented volume of accumulated heat energy and a highly loaded convective machine operating a full season ahead of schedule. Structurally, the storm has initiated a major spatial shift. While landfalling nightmare scenarios for the northern Philippines have been averted due to a critical steering shift, Mechala has commenced a long, sweeping northward and northeastward recurvature. Guided by the clockwise flow along the western boundary of a massive subtropical high-pressure ridge, the storm's trajectory now directly threatens the Sakishima Islands and Okinawa, a strategic corridor home to over 1.5 million people and critical regional infrastructure, before aiming toward the main Japanese islands near Tosa Bay on Shikoku. Yet, as the system tightens and advances, It forces a fundamental question that challenges the core assumptions of contemporary climate research. If a single patch of the Philippine Sea can supply the immense latent heat required to bootstrap a near super typhoon before the seasonal cycle has even hit its stride, what does this tell us about the hidden physical mechanisms driving the rest of the basin? And what exactly does it mean when the ocean begins to break its own limits? To fully dissect the rapid transformation of Typhoon Mechala, the analysis must shift from macro-scale observations directly into the internal mechanics of the atmospheric engine. Forecasters and atmospheric scientists operate via standardized, highly calibrated parameters, using measured, bureaucratic language designed to strip away emotional volatility. Therefore, when official projections begin utilizing terms like explosive rapid intensification, it signals a profound deviation from baseline physical models. The event that unfolded within Mechala's core on the 22nd of June represents the most hazardous structural behavior an atmospheric system can exhibit. While the textbook definition of rapid intensification requires a gain of 30 knots in 24 hours, Mechala bypassed this threshold entirely, loading its wind profile at twice the baseline velocity. The critical variable here is not merely the final kinetic force, but the severe compression of the temporal window. Human defensive systems, evacuation logistics, and coastal protection protocols rely entirely on a linear timeline to execute safety chains. When a middling convective cluster compresses a multi-day evolutionary cycle into a 12-hour window, it eliminates the operational buffer required by coastal populations. This specific velocity of intensification is precisely what transforms a manageable meteorological event into a catastrophic structural failure for human infrastructure. Mechanically, a tropical cyclone operates as a classic thermodynamic heat engine governed by the strict laws of physics. The system extracts thermal energy from the surface layer of the ocean, converts it into the mechanical energy of high-velocity winds, and expels the spent air mass through the upper troposphere. Warm water drives rapid evaporation, lifting immense columns of moisture into the atmosphere. As this vapor ascends, cools, and condenses into structural eyewall clouds, it releases vast quantities of latent heat. This thermal release directly lowers the barometric pressure at the geometric center of the storm. The resulting pressure deficit creates an intense gradient, squeezing the surrounding air mass inward and accelerating wind velocities. This feedback loop represents a storm bootstrapping itself into a highly organized monster, limited only by the exhaustion of thermal fuel or contact with a major landmass. Mechala executed this process with absolute mechanical efficiency because three critical environmental variables aligned simultaneously. The first was the absence of vertical wind shear. For an atmospheric engine to maximize its output, its internal convective column must remain perfectly stacked vertically across 10 to 12 miles of altitude. Strong upper-level winds typically tilt these columns, ventilating the warm core and disrupting the pressure drop. Mechala, however, encountered exceptionally low vertical shear, measured between 12 and 17 miles per hour, allowing the structural column to remain perfectly upright. The second variable was the exhaust mechanism at the upper boundary. The system possessed an optimal chimney effect, utilizing a localized point source aloft that efficiently evacuated ascending air masses, preventing the engine from choking on its own exhaust. The final and dominant variable was the deep oceanic fuel source. While wind shear and upper-level venting are highly volatile atmospheric elements that fluctuate daily, ocean heat represents the deep, slow memory of the climate system. The sea surface temperatures along Mechala's track were measured between 29 and 30 degrees Celsius, or 84 to 86 degrees Fahrenheit. This is a full 3 to 4 degrees above the critical 26.5 degree threshold required to sustain a tropical cyclone. In the calculus of fluid dynamics, This thermal anomaly represents a massive surge in available kinetic potential. Furthermore, this warmth was not a superficial skin layer. When a major storm churns the ocean surface, its mechanical force induces intense vertical mixing, typically pulling cooler deep water upward to act as a natural thermal break. Mechala, however, did not experience this self-limiting cooling. The deep ocean heat content ran exceptionally deep, ensuring that the vertical mixing loop continuously fed high-temperature water into the engine, sustaining its explosive acceleration. This extreme accumulation of deep thermal energy directly reflects the broader macrostate of the Pacific Basin, which has undergone a rapid cyclical transition. Over the preceding 6 months, the Tropical Pacific Index swung dramatically from a cool negative 0.55 to a warm positive 0.48, rapidly shifting the entire basin toward a heavily loaded, high-energy state. This thermodynamic reality completely deconstructs the alternative narratives and superficial myths that inevitably propagate across digital networks during major geophysical events. Superficial interpretations frequently attribute such unprecedented early-season storms to deliberate weather modification, localized geoengineering, or ionospheric heating facilities. These claims collapse immediately when evaluated against the fundamental energy budget of the system. The latent heat released daily by a mature typhoon like Mechala outproduces the entire collective electricity generating capacity of human civilization by a factor of hundreds. Human engineering possesses no mechanism capable of generating, nudging, or maintaining localized energy on this scale. It is an physical impossibility. Similarly, assertions that the storm's sharp turn toward Okinawa implies artificial steering are disproven by the clear documented presence of the subtropical ridge, whose clockwise boundary flow has dictated identical recurvature paths for millenniums. The parallel claims that national agencies are actively concealing the storm's true intensity are dismantled by the transparent multi-agency tracking framework itself. The variation in wind estimates between the Joint Typhoon Warning Center, the Japan Meteorological Agency, and Pagasa is not an evidence of obfuscation, but a standard, openly disclosed scientific reality of estimating high-velocity systems via remote satellite imagery. Even the multiple designations, Mechala, Francisco, and Storm 7, are merely the logical consequence of independent regional agencies executing transparent tracking protocols in the open. The reality is far more challenging than a hidden human hand. The Pacific Ocean has simply become an exceptionally warm, highly loaded system capable of manufacturing top-tier structural anomalies entirely on its own. The physical trajectory of Typhoon Mechala across the Western Pacific brings the analytical focus directly to the geographical impact zones, where fluid dynamics intersect with concrete human infrastructure. Pushed relentlessly along the western boundary of the subtropical ridge, Mechala is executing a classic meteorological recurvature, transforming from an open ocean thermodynamic curiosity into an immediate structural threat to the island chains of southern Japan. The forward velocity of the system holds steady at approximately 20 kilometers per hour as it advances across the Philippine Sea. The primary geographical targets in the immediate firing line are the Sakishima Islands, representing the southwestern terminus of the Ryukyu Arc, followed immediately by Okinawa's main island. These coordinates are not abstract points on a tracking chart. They represent highly developed, high-density hubs of human civilization and regional logistics. Okinawa alone supports a population of over 1.5 million people and hosts critical infrastructural networks. Because of its geographic vulnerability, this region operates under some of the most stringent engineering and construction codes globally. The structural memory of previous encounters has forced the integration of heavy defensive measures into the local architecture. Yet, while this systemic preparedness mitigates mass casualties, it does not guarantee invulnerability against a system that has demonstrated such rapid energetic accumulation. The structural hazards delivered by a major typhoon manifest in distinct interconnected physical layers. The outermost layer is the wind field itself, capable of transforming unanchored objects into high-velocity projectiles and disrupting regional electrical grids. Beneath the wind field lies the storm surge, a massive wall of seawater, displaced by the storm's low central pressure, and forced landward by the kinetic energy of the eye wall. For an island ecosystem, the storm surge is exceptionally hazardous because spatial constraints eliminate any true inland buffer. There is no point on these landmasses isolated from the marine boundary. Concurrently, the vertical convective columns pump immense volumes of water vapor skyward, resulting in torrential rainfall measured in feet rather than inches. When this volume of water impacts the steep, elevated topography of the Ryukyu chain, it rapidly triggers flash flooding and systemic slope failures. Currently, official forecasting models project a gradual attenuation of Mechala's maximum winds as it climbs past the Ryukyu Islands and approaches the main Japanese islands near Tasa Bay on Shikoku. This projected decay is driven by standard atmospheric transitions. As a storm moves into higher latitudes, it inevitably encounters cooler sea surface temperatures and an escalating profile of vertical wind shear, which acts to unstack the storm's core. However, an honest scientific assessment requires acknowledging the deep margins of uncertainty built into these fluid models. The rate of decay depends entirely on the precise temperature profile of the water column along its path and the exact timing of the atmospheric shear acceleration. A slight variation in these factors could allow the storm to retain its catastrophic profile far longer than predicted. This forecasting volatility is further compounded by a highly complex internal mechanism known as an eye-wall replacement cycle. In top-tier systems, the intense inner ring of thunderstorms surrounding the eye frequently becomes unstable and is enveloped by a secondary outer convective ring. As the outer ring constricts, it chokes off the moisture supply to the inner core, causing a temporary drop in peak wind velocity. However, once the new outer eye wall stabilizes and consolidates, the system can rapidly re-intensify, often expanding its total kinetic footprint over a wider geographic area. This internal restructuring means a storm's intensity can fluctuate dramatically within a 24-hour window, complicating defensive preparations on the ground. This scientific uncertainty must not be confused with institutional failure or deliberate deception. The honest representation of a typhoon's path is never a single line, but a widening cone of probability. To evaluate the true systemic implications of Mechala, analysts must look directly at the 22-year historical baseline established by Super Typhoon Dianmu in June of 2004. Dianmu achieved an even lower central pressure of 915 hectopascals and sustained winds reaching up to 180 knots, demonstrating the absolute upper limit of the basin's capacity during an out-of-season month. This historical analog offers a vital dual realization. First, it demonstrates that early-season super typhoons, while statistically rare, are fundamentally bound by the natural distribution of the basin's thermodynamic history. The planetary system is not experiencing an impossible violation of physical laws. Second, and more critically, the 2004 season serves as a stark structural warning. Dianmu was not an isolated anomaly in a quiet year. It was the explosive opening act of one of the most volatile, destructive, and active typhoon seasons in modern history, which ultimately produced 6 super typhoons. The deep ocean heat content that allowed Dianmu to detonate in June did not dissipate. It persisted through August, September, and October, continuously feeding subsequent systems. While a single historical analog cannot function as a literal crystal ball for the current year, the underlying physics of ocean heat persistence remains absolute. The heavily loaded, thermally elevated Pacific basin that manufactured Mechala in the third week of June will remain present, providing a massive reservoir of latent energy for every tropical system that follows. Mechala is an early measurement of a highly charged planetary system, and the baseline data indicates that the structural limits of the basin are being tested far ahead of schedule. The structural analysis of Typhoon Mechala must culminate in a sober evaluation of the systemic interface between advancing geophysical forces and the psychological frameworks of human observers. As the storm executes its precise geometric curve across the coordinate grid of the Philippine Sea, it exposes a distinct cognitive vulnerability within human systems. When confronted with an event that shatters established calendar expectations and historical baselines, society frequently splits into competing, non-empirical narratives. On one side stands the superficial impulse to declare this single June typhoon an absolute, definitive proof of immediate planetary collapse. This perspective elevates Mechala into an ideological smoking gun, using emotional language to assert that the natural order has completely broken down. An objective systems analysis reveals this to be a fundamental logical error. A single meteorological data point, no matter how extreme or temporally displaced, cannot mathematically validate a sweeping macro-level conclusion. To claim an isolated event proves an ultimate global catastrophe is to ignore the rigorous, patient methodology of long-term statistical aggregation that defines genuine climate research. Conversely, this emotional overreach triggers an equally unscientific counter-narrative rooted in denial and the fabrication of artificial causes. By failing to grasp the sheer mathematical scale of the forces at play, superficial commentators lean on conspiratorial frameworks to explain away the anomaly, refusing to confront the documented shifting baselines of our oceans. Both extremes make the identical analytical misstep. They reject the hard, disciplined work of analyzing fluid mechanics, energy budgets, and atmospheric pressure gradients in favor of immediate, pre-packaged certainty. The true crisis revealed by Mechala does not require the invention of secret weapons, nor does it demand apocalyptic hyperbole. The reality sitting in plain sight within the sea surface temperature datasets is far more profound and structurally challenging. The underlying data demonstrates a measurable, persistent elevation of ocean heat content running deep beneath the marine boundary layer. This deep thermal reservoir is an objective physical reality, accumulating slowly over months and years, functioning as the deep memory of a changing planetary budget. When an early season system like Mechala encounters a basin in this highly charged state, the result is governed entirely by the laws of thermodynamics. The ocean possesses a massive, authentic surplus of latent heat energy, and it is fully capable of manufacturing top-tier structural anomalies completely on its own, without a human author and without an external off switch. This realization is inherently more unsettling than any conspiratorial myth, because it means the natural systems themselves are operating under heavily loaded parameters that human infrastructure must now routinely endure. As the storm advances toward the critical logistical nodes of Okinawa and the Japanese mainland, it leaves behind a clear empirical record. The 22-year benchmark established by Super Typhoon Dianmu in 2004 remains a stark mechanical reference class. It reminds us that while the planetary machine is capable of generating these extreme out-of-season forces through natural statistical variance, such early detonations are often the structural overture to highly volatile seasonal cycles. The persistent ocean warmth that loaded the dice for Mechala will not magically dissipate. After its passage, it remains anchored in the Western Pacific, waiting to interface with every subsequent convective cluster that enters the basin during the peak months of August, September, and October. For engineers, emergency managers, and regional planners, the takeaway is clear and non-negotiable. The operational boundaries of our defensive systems must be recalibrated to account for the compression of forecasting windows and the increasing frequency of explosive rapid intensification. We are witnessing the tangible manifestation of structural limits being tested by an accelerated energy cycle. Mechala is not a harbinger of an immediate mechanical end to the world, nor is it a manufactured illusion. It is a highly organized, natural thermodynamic engine running at maximum output over a primed ocean, serving as an explicit, data-driven warning of what it looks like when a macroecological system begins to reveal its true, unyielding power ahead of schedule. The ultimate evaluation of Typhoon Mechala requires a final synthesis of the operational boundaries governing both the atmospheric machine and the human structures built in its path. As the system enters the final phases of its projected track, moving past the high-density infrastructure of the Ryukyu Islands and advancing toward the mainland waters of Tasa Bay on Shikoku, the cascading effects across all systemic levels become fully manifest. At the microcomponent level, the internal physics of the storm continue to dictate its interface with the surrounding environment. The mechanical breakdown of the system is not an arbitrary event, but a strict function of entering higher latitude fluid dynamics where the thermal reservoir begins to thin. Yet, even as the storm experiences the unstacking forces of increased vertical wind shear, the deep memory of the ocean heat it absorbed in the Philippine Sea remains the dominant driver of its structural persistence. This lingering energy buffer directly challenges the defensive calculations of human emergency management networks. The primary lesson embedded in Mechala's behavior is the absolute collapse of the temporal buffer. When an early season system compresses its intensification cycle into a 24-hour window, it exposes the structural vulnerability of linear human planning. Evacuation routes, regional supply lines, and civil defense protocols are fundamentally designed around predictable, gradual warning timelines. Mechala has effectively demonstrated that a highly charged basin can bypass these operational expectations entirely, forcing coastal communities to confront a top-tier hazard with minimal preparatory lead time. This is where the human factor intersects directly with the physics of the crisis. The danger escalates not just because the winds are faster, but because our organizational systems require time that the thermodynamic engine no longer provides. Furthermore, the deconstruction of alternative narratives remains essential to understanding the true limits of our contemporary situation. Throughout the life cycle of this storm, superficial interpretations have consistently sought to frame the event through lenses of external control or immediate planetary doom. These frameworks are definitively invalidated by the rigid constraints of the planetary energy budget. A natural system that casual observers label as an impossible anomaly is in reality a highly efficient fluid engine operating precisely within the bounds of its available thermal fuel. Human infrastructure cannot negotiate with, steer, or mitigate an energy release that outpaces our collective industrial output by a factor of hundreds. The true, sobering reality is that the natural systems are simply adapting to a higher baseline of accumulated energy, and they are executing their thermodynamic functions with absolute indifferent efficiency. This brings the entire investigation to a definitive structural conclusion grounded in the limits of the Western Pacific Basin. The historical reference class of 2004 and the rapid 6-month swing of the Tropical Pacific Index to a warm positive 0.48 demonstrate that Mechala is not a temporary fluke of the week, but a baseline readout of a fundamentally altered system. The immense volume of deep ocean heat content that enabled this June detonation remains anchored in the upper layers of the sea. It will persist long after Mechala dissipates into the higher latitudes, serving as a ready fuel source for every subsequent convective cluster that forms throughout the peak months of the seasonal cycle. The boundaries of the system have been explicitly redrawn. Human civilization is no longer operating within the comfortable historical calendar parameters of the past century. We are now forced to interface with a natural machine that is loaded, primed, and capable of generating maximum mechanical output ahead of schedule. Typhoon Mechala stands as an enduring, data-driven marker of this transition, a cold, empirical demonstration of the rigid architectural limits of our natural world, and a stark reminder that the oceans carry a deep, turbulent memory that